Everyone, it's Mr. Edie back with yet another video. Today, guys, we're going to be talking about how we calculate the equilibrium constant. So as you know, thus far, we've only been writing the equilibrium constant in terms of its algebraic expression, right? Well, today we're going to go through and actually calculate and get a finite number for it, okay? So the most direct way to calculate the equilibrium constant is to use the concentrations of the reactants and products measured obviously at equilibrium, okay? Um, the equilibrium constant does depend on temperature, so keep that in the back of your mind. That's why, if you notice, guys, on all the practice problems we've been doing and all the example problems we've been working out together, I always list the temperature in which that equilibrium is occurring at, because the equilibrium constant does depend on temperature. Kc is unitless because the units in the expression are molarity, therefore they will cancel out. For any reaction, the equilibrium concentrations depend on the initial concentrations. That's important. And then the equilibrium constant itself is constant at a given temperature, regardless of those initial concentrations. So let's take a look at that in a little bit more detail. So here, guys, we have a chemical equilibrium. We're back to our H2 and I2 is in equilibrium with HI. We've been, of course, looking at this equilibrium since the start of the unit. But in this case, guys, we have some experimental data. We have 5 different trials. And you'll notice in each trial, I start at different initial concentrations for my reactants and products. So in each trial, again, the concentrations are different. And those initial concentrations had a direct impact on my final concentrations, right? So if you take a look here, all the equilibrium concentrations are different from each trial. And again, that's because equilibrium concentrations are dependent upon the initial concentrations. With that being said, because this chemical equilibrium is occurring at 445 degrees Celsius, right? That's what the temperature where in which this reaction is occurring at. You'll notice that the equilibrium constant for each of these trials is in fact 50, right? We go down the line here, it is 50 across the board. Okay. Now that's important because, folks, guess what? That is exactly what we expect. This reaction is occurring at 445 degrees Celsius. Therefore, these concentrations should have the same equilibrium constant because the temperature was constant. All right. Let's dive in and do an actual practice problem here. So still considering the same equilibrium, we have suppose a mixture of H2 and I2 is allowed to come to equilibrium at 445 degrees Celsius. The measured equilibrium concentrations of H2 include 0.11 molar, and then I2 is 0.11 molar, and then HI is 0.78 molar. Our question here is, what is the value of Kc for this given temperature, right? So again, guys, the way that we would solve this is we would just start off by writing our equilibrium expression. So Kc is equal to the concentration of Hi raised to the second power because of its stoichiometric coefficient over the concentration of H2 times the concentration of I2. Notice that their stoichiometric powers are each 1, so that's why I'm not writing anything. And then from here, guys, since we are given these equilibrium concentrations, I can get ahead and plug them right into my equilibrium constant expression. So I'm going to have 0.78 raised to the second power over the concentration of H2, which is 0.11 molar, times the concentration of I2, which also is 0.11 molar. We plug this into our calculator. So 0.78 raised to the second power over 0.11 times 0.11. We indeed get 50. I'm going to put a decimal point here to let you know that I want that 0 to be significant. And that is our equilibrium constant here. So, guys, you'll notice that that was a very pretty straightforward approach on how we would calculate our equilibrium constant, right? Once we write the equilibrium expression, we plug in our equilibrium concentrations, and then, put it in the calculator and then calculate it out. We got our equilibrium constant. You'll also notice that 50 here is the same value for our equilibrium constant because, of course, this particular for the same equilibrium from the previous slide occurred at the same temperature. So we are expecting it to be 50, right? But beyond that, guys, very straightforward once we know these equilibrium concentrations, right? The question is it always this straightforward? And I got to say, unfortunately, it's not. Sometimes we're given the initial concentrations with only one equilibrium concentration. And then the question is, well, what do you do then? And let's talk about that. So in order to calculate Kc, we need a couple things. The first thing we need is a balanced chemical equation. So once we have a balanced chemical equation, guys, we can that will set us up for writing, of course, the equilibrium constant expression. From there, we need to know the initial concentrations of our reactants and products. Once we know those, we only need to know one equilibrium concentration, and that could be for one reactant or one product, because we can use stoichiometry to fill in the rest. So again, what do we need? Balanced chemical equation. We need the initial concentrations of the reactants and products, and then we need the equilibrium concentration for a reactant or the equilibrium concentration of a product. We're going to use stoichiometry to fill in the rest. Now, we've got 4 steps for calculating Kc. Step number 1 is we're going to write the balanced chemical equation. Once we have that, we will write an equilibrium constant for the expression. Then we're going to throw our concentrations into the ice box. So here, guys, we're given this ice box. Ice will stand for our initial concentrations. Change will be C. Okay, and then equilibrium, of course, is E. So that's how we get ice. Here, you guys are noticing I have A is in equilibrium with B. So those are my concentration of my reactants would be a concentration of A. My products would be my concentration of B. And then I would write their initial concentrations in here. The change would be what's being involved with their stoichiometry. And then finally, the equilibrium would obviously be their equilibrium concentrations. So we'll throw our expressions into the ice box. And then, guys, we will use stoichiometry to solve for the change. And then, of course, we'll find our equilibrium concentrations. Oops. Once we have our equilibrium concentrations, the actual numbers from using the ice box, we'll plug those into the Kc expression, and then we calculate. So pretty simple here, just 4 steps in order to get Kc. So let's start. So it says, considering the following chemical reaction, we have carbon monoxide is an hydrogen gas is in equilibrium with methanol gas. Okay, guys. It says the reaction mixture at 780 degrees Celsius initially contains a concentration of 0.500 molar of carbon monoxide and 1 molar concentration of hydrogen gas. At equilibrium, the carbon monoxide concentration is found to be 0.15 molar. And then we have to ask ourselves, what is the value of the equilibrium constant? All right, so let's dive right into this problem here. So step 1 is to see if we have a balanced chemical equation. And let's take a brief moment and see if we do. We, in fact, do, right? We've got 1 carbon on both sides of the equation here. We have 1 oxygen on both sides of the equation. And then 4 hydrogen. So our balanced chemical reaction is indeed here. Step 2 is to write down our equilibrium expression. So we're going to say Kc is equal to the concentration of our product. In this case, it's methanol. So CH3OH goes on top. And then we're going to put it over the concentration of CO times the concentration of H2 raised to the second power. So that's step 2's out of the way. And now step 3 is going to be creating our ice box. I have my ice box drawn, everybody. We're going to plug in what was given to us in the problem. So one things first, guys, is the units for an ice box is, of course, molarity or atmospheres. All right, so units for an ice box is going to be either molarity Okay, so M, or for atmospheres. Now, this would, of course, depending if we're given concentration or if the problem is giving us pressure. Okay, so keep that in mind, but that's what our units would be inside the ice box, dependent upon what we've got going on. Now, uh, the concentration initially of carbon monoxide is 0.500 molar. The concentration of hydrogen gas is 1.0 molar. Okay. And then methanol was 0, right? They didn't tell us what that methanol concentration was. So we're going to assume it is in fact 0. We don't know anything about change yet because they didn't tell us the change. Instead, they told us that carbon monoxide's equilibrium concentration was in fact 0.15 molar, which means that in order to go from 0.5 molar to 0.15 molar, we lost, or 0.35 molar, excuse me, folks, was missing, right? It reacted. So now that we know that 0.35 molar of carbon monoxide is reacting, right? That's how much concentration reacted in this particular equilibrium. We can now determine the change for our hydrogen gas and then the change for our uh, methanol, right? So, with that in mind, guys, when we're working in an ice box, we divide by the number we're in. So, we divide by the stoichiometric number we're in. So, remember, there's really an invisible 1 in front of carbon monoxide. And then we multiply by the number we're going. So, I'm going to say, okay, we got 0.35 divided by 1 because that's the column we were in, but I'm going to hydrogen, so I'm going to multiply this value by 2. So in this case, we're going to have 0.70 molar of our hydrogen gas that's reacting. And this is going to be negative 0.70 molar because it's part of the reactant. So I'm going to subtract. So 1 molar minus 0.70 is going to be 0.30 molar. Okay. And then same idea here, guys. Now that we know the change of our carbon monoxide, I'm going to take this number and I'm going to multiply. I'm going to divide by the column I'm in and multiply by the column we're going. Well, the column I'm going to has an invisible 1 in front of methanol. So I'm going to do 0.35 divided by 1 times 1, which of course is going to be 0.35 molar. And because this is our product, it's going to be positive because this is currently being produced. So we have 0.35 molar of methanol at equilibrium. Now that I know my equilibrium constants, everybody, okay, I can use this to calculate Kc. So Kc is going to equal the concentration of methanol at equilibrium, which is 0.35 molar, over the concentration of carbon monoxide, so 0.15 molar, times the concentration of H2, which is 0.30 molar squared. And now I'm going to plug this expression into my calculator, and I'm going to get my value of Kc. Once I do that, I get an equilibrium constant value of 26. And that, of course, is my final answer. So to recap what we did here is first thing first is we checked to see if we had a balanced chemical equation. Once we checked that, we wrote the equilibrium constant expression Kc. So Kc in this case was the concentration of methanol over the concentration of carbon monoxide times the concentration of H2 squared. Then we drew our icebox, right? We plugged in our initial concentrations, which in this case was 0.5 molar for carbon monoxide, 1 molar for H2, and then 0 molar for methanol. And we plugged in our equilibrium concentration for carbon monoxide, which was 0.15 molar. Once we did that, guys, I looked to see what my change was between my initial concentration of carbon monoxide to my equilibrium concentration of carbon monoxide. That's how we got 0.35 molar. Once I knew what my change was, I used that changed value to get to my equilibrium, to get my change concentrations for hydrogen gas and methanol, respectively. And then I subtracted for hydrogen because it was a reactant, so it's being used up. That's how I arrived at 0.30 molar. And then I added for methanol because, of course, it was a a product. That being said, then finally we plugged in our equilibrium concentrations uh, into our equilibrium expression and then plugged this into our calculator, got our final number of 26. All right, guys, we're going to move into our next problem here, which is going to be you do, we review. Okay, so that says, considering the following equilibrium, we have methane is in equilibrium with C2H2, which would be ethine, and hydrogen gas. And it says, the reaction mixture at 1700 degrees Celsius initially contains a concentration of methane of 0.115 molar. At equilibrium, the mixture contains a concentration of ethine, C2H2, of 0.0035 molar. And then it wants us to calculate the value of the equilibrium constant. So, go ahead, guys, pause the video, try to solve this problem on your own, and then unpause it to see if you did it correctly. All right, everyone, and I hope you were able to get an equilibrium constant value of 0.020. Okay. So guys, this problem here, very similar in terms of how you would solve it to our I do problem on the previous slide. I want to go through a recap with you to show you how I did and how I solved this. Okay, so the first thing I did, guys, was check to see if we had a balanced chemical equation. We indeed did. This chemical equation is in fact balanced. Step 2 then was to write the value of Kc for this equilibrium. So we have the concentration of C2H2 times the concentration of H2 to the third power, all over the concentration of CH4 squared. From there, I drew my ice box, okay, and I plugged in the information that was given to me. So keep in mind, they informed us that the concentration of our methane was 0.15 molar, 0.115 molar. That was our initial concentration. They didn't tell us our initial concentrations of C2H2 and H2, but since they didn't, we're going to assume that both of those concentrations initially were 0 molar, so that's where those zeros come from. Then they did give us the equilibrium concentration of C2H2, which was 0.035 molar. Okay, so that was all given to us, what's being underlined and squared in pink. That means that the change of our C2H2 was it added 0.035 molar. So I use this number here to determine what the change was for H2. So I used stoichiometry. So I divided by the column we were in. So that's where an invisible 1 will come in. And then I multiplied by the column I was going to. So there was a 3 in front of H2. So I did 0.035 divided by 1 times by 3. And I got a change of 0.105. I'm adding this number because products are produced, and that's how I got my equilibrium concentration of H2. Now, conversely, as I was trying to find my equilibrium concentration of CH4, I had to take the change again. And the change here, I divided by 1 because that was the column I was in. Okay. Then I was going to C2H2, so I multiplied by 2. So that's where 0.035 divided by 1 comes from. Then multiplied by 2. I get a 0.070 as my value. Now here, what I'm going to do is I'm going to subtract this from my initial concentration because reactants are used up And when I do so, I get an equilibrium concentration of 0.045 molar. From there, guys, I can plug all these values into my equilibrium constant, and then I plug that into my calculator, and I got 0.020 as my final answer. And with that being said, folks, that's the end of today's video. If you have any questions, of course, shoot me an email.